Every physicist agrees on how old the universe is, until you ask them to measure it directly. Then two of the most respected research teams on the planet, using two completely different methods, arrive at two different answers. Not wildly different, not off by a factor of 2, off by about 6%. In most fields of science, a 6% disagreement would barely raise an eyebrow. In cosmology, where a single number underpins the age, the size, and the fate of everything that exists, a 6% gap has turned into one of the most serious unresolved problems in modern physics. The number in question is called the Hubble constant. It describes how fast space itself is stretching apart right now, today, at this very moment. Not how fast it was expanding a billion years ago. Not some theoretical future rate. The present tense expansion rate of the entire observable universe, compressed into a single figure. You would think a number like that, once measured carefully by two competent teams, would converge. Science usually works that way. You refine your instruments, you tighten your error bars, and eventually independent measurements shake hands. That is not what has happened here. The disagreement has survived better telescopes, better statistics, and an enormous amount of scrutiny from some of the most careful observers in the field. If anything, the gap has gotten harder to explain away. Not easier to understand why this number matters so much. It helps to start with something simpler. The basic fact that the universe is expanding at all. In the 1920s, an American astronomer working at the Mount Wilson Observatory in California pointed a telescope at distant galaxies and noticed something strange. Their light was shifted toward the red end of the spectrum, and the more distant a galaxy appeared to be, the more its light had shifted. Stretched light, in this context, means the wavelengths of that light have literally been pulled longer as space, expanded during the journey from that galaxy to our telescope. The relationship was almost mechanical in its simplicity. Distance and redshift climbed together in near lockstep. The conclusion was staggering. The universe was not static. It was not eternal and unchanging, the way nearly every scientist before that point had assumed. Space itself was stretching, carrying galaxies apart from one. Surface of a balloon spread apart as the balloon inflates. That astronomers' original calculation for the expansion rate turned out to be badly wrong, off by nearly a factor of 10. So far off that it implied the universe was younger than the rocks sitting beneath his own observatory. It took decades of refinement, arguments between rival camps of astronomers, and generation after generation of better instruments before the field settled on a number anywhere close to correct. By the turn of the millennium, most researchers had converged on a value somewhere around 70 kilometers per second per megaparsec, with the argument mostly resolved. A megaparsec is roughly 3,260,000 light-years. So that number means for every 3,260,000 light-years of distance you look outward, the galaxies out there are receding from us about 70 kilometers every second faster than the galaxies closer in. It felt for a while like a settled question. Then the instruments got sharp enough to expose a second, quieter disagreement sitting underneath the first one. And this new disagreement has proven far more stubborn than anyone expected. There are two fundamentally different ways to measure how fast the universe is expanding today, and they approach the problem from opposite directions in time. The first method looks at the deep past and calculates forward. Shortly after the Big Bang, the universe was an opaque, blazing hot soup of particles, too dense for light to travel freely. Roughly 380,000 years later, It had cooled enough for electrons and protons to combine into neutral atoms, and space suddenly became transparent. The light released at that moment has been traveling through the universe ever since, stretched by billions of years of cosmic expansion into faint microwave radiation that now fills the sky in every direction. We call it the cosmic microwave background, and it is essentially a baby picture of the universe, taken when it was less than 400,000 years old. A European Space Agency mission called Planck spent roughly 4.5 years mapping that afterglow in extraordinary detail, measuring tiny temperature fluctuations across the sky that revealed the density variations present in the infant universe. Feed those measurements into the standard cosmological model, the mathematical framework that has successfully predicted the abundance of light elements, the large-scale structure of galaxies, and the pattern of that microwave background itself. And you can run the equations forward across nearly 14 billion years to predict what the expansion rate should be today. The answer that calculation produces is about 67 kilometers per second per megaparsec, with a remarkably small margin of error. This is a prediction, not a direct measurement. It assumes the standard model is complete and correct, then extrapolates. The second method does not extrapolate from the deep past at all. It measures the present universe directly, using a technique astronomers call the cosmic distance ladder. It works by chaining together several methods of measuring distance, each one calibrated by the one before it, extending outward from our cosmic backyard to galaxies, hundreds of millions of light years away. The first rung of that ladder relies on a class of stars called Cepheid variables, stars whose brightness pulses in a rhythm directly tied to how luminous they actually are. Measure how quickly a Cepheid brightens and dims, and you can calculate its true, intrinsic brightness. Compare that true brightness to how dim the star appears from Earth, and basic physics gives you the distance, because light fades in a precisely predictable way as it travels. Astronomers have been using this trick since the early 20th century, when an astronomer named Henrietta Leavitt first discovered the relationship while cataloguing thousands of variable stars. The next rung climbs to galaxies that contain both Cepheids and something else, a specific class of exploding stars called Type 1a supernova. These stellar explosions occur when a dead star called a white dwarf pulls in enough extra material from a companion star to cross a specific mass threshold, triggering a runaway thermonuclear detonation. Because that threshold is essentially the same everywhere in the universe, these explosions reach almost identical peak brightness no matter where they occur. Once you calibrate their true brightness using Cepheids sitting in the same galaxy, you can spot these supernova in far more distant galaxies, measure how dim they appear, and calculate distances hundreds of millions of light years out, far beyond where individual Cepheids could ever be resolved. Combine those distances with how quickly those distant galaxies are receding from us. Information astronomers get simply by measuring the stretching of their light, and you arrive at a direct, present-day measurement of the expansion rate. A team led by the astronomer Adam Rees, working under a research program called SHOES, has spent more than 2 decades refining exactly this measurement. Their result, about 73.6 kilometers per second per mega, not 67, 73.6. That gap, roughly 6 or 7%, might sound trivial. It is not. In a field where individual research teams now claim precision within about 1%, an 8 or 9% disagreement between 2 independent, carefully checked methods is enormous. It is the difference between a universe that is roughly 13.8 billion years old and one that could be well over 1 billion years younger. Every downstream calculation shifts along with it. The size of the observable universe, the separation between galaxy clusters, the timeline for when the first stars ignited, when the first heavy elements were forged inside dying stars, when conditions suitable for planets and chemistry and eventually life first became possible. You are not adjusting a small dial on a dashboard. You are quietly redrawing the timeline of everything that has ever happened. For years, the leading explanation was that somebody, somewhere, had made a measurement error. The most popular candidate was a problem called stellar crowding. Cepheid variables tend to live inside the dense, dusty spiral arms of younger galaxies, regions packed with other stars. Older telescopes sometimes struggled to separate a single Cepheid from its crowded neighborhood, blending its light together with nearby stars and making it appear artificially brighter than it truly was. A Cepheid that looks brighter than it really is gets assigned a shorter distance, and a shorter distance pushes the calculated expansion rate higher. If that blending could be cleaned up with a sharper telescope, the argument went, the tension between the two measurements should quietly relax back toward agreement. That hope rested almost entirely on one instrument, a space telescope launched at the end of 2021, orbiting roughly 1,500,000 kilometers from Earth, in a stable position beyond the interference of our planet's atmosphere and heat. Its mirror, 6.5 meters across and coated in a thin layer of gold, was built to collect infrared light with a sensitivity that dwarfs anything that came before it. If any instrument could resolve individual Cepheids cleanly enough to settle the argument, this was it. Infrared light cuts through the dust that clouds visible light observations, and a sharper view was expected to reveal the crowding, correct the distances downward, and pull the expansion rate back toward the value predicted from the early universe. Some astronomers were reportedly already treating the disagreement as good as resolved, before the new data had even been analyzed. That is not what happened. When the new observations came in, they confirmed the original numbers almost exactly. The Cepheids looked the same. The distances held. The expansion rate stayed close to 73. In early 2024, the SHU's team published a paper extending their Cepheid observations out to a galaxy, roughly 130 million light-years away, using more than 1,000 individual Cepheid stars spread across 5 host galaxies of 8 separate supernovae. Their conclusion was blunt. Measurement error from crowding could be ruled out with very high confidence. As Rees put it afterward, with the most obvious sources of error eliminated, what remains is the possibility that our model of the universe is missing something. There is a moment from a few years earlier that captures how seriously some physicists were already taking this. At a conference at a theoretical physics institute in California, Rees asked a Nobel laureate in particle physics whether the field should start describing the disagreement as a genuine problem. The answer he got back was sharper than that. Not a tension, not a problem. A crisis. By the end of 2024, that crisis had only deepened. The SHU's team published their largest analysis yet, drawing on data collected across the telescope's first 2 years of operation. This time, they used 3 separate, independent methods to measure distances to the same supernova host galaxies. The original Cepheid technique, a method using carbon-rich stars, and a completely different approach known as the tip of the red giant branch, which relies on the predictable maximum brightness reached by aging stars, just before they undergo a sudden internal shift in how they generate energy. All three methods agreed with each other, and all three continued to point toward a universe expanding faster than the early universe model predicts. So either the standard model of cosmology is missing an ingredient, or there is a piece of physics operating somewhere in the 14 billion years between the early universe and today that nobody has properly accounted for yet. Not every astronomer is convinced the tension is entirely real, at least not in its full strength. An astronomer at the University of Chicago named Wendy Friedman has spent years building an independent version of the distance ladder that relies less heavily on Cepheid specifically. Her approach leans more on red giant stars and a separate class of stars found in less crowded regions of their host galaxies. Stars that are less vulnerable to the exact blending problem the newer telescope was supposed to resolve. When her team published their own analysis in the middle of 2024, the three separate methods she used did not fully agree with each other. Two of them landed closer to 68 or 70, consistent with the value predicted from the early universe. Her Cepheid-based measurement came in higher, closer to 72, though with larger uncertainty attached. Combined together, her overall results sat around 70, uncomfortably positioned in the gap between the two. Rival camps rather than clearly siding with either one. A Nobel Prize-winning cosmologist who reviewed her results before publication pointed out something worth sitting with. Her data suggests there may be tension hiding within the star-based distance measurements themselves, even before you compare any of them to the early universe prediction. That is a different, arguably more troubling kind of problem. It suggests the distance ladder itself, the tool astronomers have relied on for roughly a century to map the nearby universe, might carry unresolved uncertainties at its foundation that no single telescope, however sharp, can fully untangle. Rees and his collaborators have pushed back on Friedman's conclusions, arguing that her sample of supernovae was smaller and potentially less representative than their own, which could bias her results towards the lower end. The disagreement between these two research groups has become one of the more closely watched scientific rivalries in modern physics. Two extremely careful teams, looking at the same sky, drawing different conclusions about what that sky is actually telling them. One idea that keeps resurfacing as a possible resolution is something called early dark energy. The hypothesis proposes that a brief, extra burst of cosmic expansion occurred sometime in the first few 100,000 years after the Big Bang, then faded away and left no obvious trace afterward. If something like that really happened, it would subtly alter the conditions imprinted in the cosmic microwave background, nudging the early universe prediction for the expansion rate upward, closer to the value the distance ladder measures directly. Without breaking any of the other predictions the standard model gets right. A cosmologist at Johns Hopkins University, who has helped develop this idea, has compared it to the universe receiving an unexpected kick immediately after it was born, a nudge that rippled forward through nearly 14 billion years of subsequent expansion and subtly altered the number we measure today. Nobody has detected direct evidence that early dark energy actually existed. No experiment has confirmed it, but it remains one of the few proposed solutions capable of resolving the tension without demolishing everything else. The standard model successfully explains the expansion rate. Disagreement would be enough on its own to keep cosmologists awake at night. But the same telescope that reignited that argument delivered a second, entirely separate shock almost as soon as it began observing. It found galaxies in the early universe that, according to the standard model, should not have existed yet. not small, faint, barely formed protogalaxies, which is exactly what the standard model predicts should be visible at those distances. Massive ones. Fully formed looking galaxies, observed as they appeared just 500 to 700 million years after the Big Bang, some of them rivaling the mass of our own galaxy. Building a galaxy the size of the one we live in took our cosmic neighborhood roughly 13 billion years. These distant galaxies appeared to have assembled themselves in under a billion. An astronomer at the University of Texas at Austin ran the numbers carefully in a study published in a leading astronomy journal, looking at 6 of the earliest and most massive galaxy candidates the telescope had found. He showed that they pushed right up against the absolute physical limit of what the standard model of galaxy formation allows. To build galaxies that heavy, that quickly, nearly every atom of gas sitting inside their surrounding halos of dark matter would have needed to convert directly into stars. In a typical, well-behaved galaxy, that conversion efficiency sits somewhere around 10%. The remaining 90% of available gas simply never gets around to forming stars. It is too hot, or radiation blows it back out into space, or it drifts away before gravity can pull it together. These newly discovered galaxies appeared to be operating at something close to 100% efficiency, as though every scrap of raw material available to them had been converted into finished stars with essentially zero waste. That is not how star formation is supposed to work in any model astronomers had built up to that point. The initial reaction across the field was, understandably, alarm. If galaxies really were forming this massive this quickly, then either the models describing how galaxies grow were deeply incomplete, or something more fundamental about the standard cosmological framework needed revision. A few physicists floated the idea that unknown particles or forces might have been at play in the early universe, accelerating star formation far beyond what current models allow for. Then came a significant correction. A graduate student at the same university in Texas led a follow-up study published in the middle of 2024 that took a much closer look at the data behind these apparently oversized galaxies. What she found was that many of them were not what they first appeared to be. Their brightness was being inflated by something else entirely, the black holes sitting at their centers. These particular objects had already picked up a nickname among astronomers: little red dots, a reference to their compact size and reddish color as seen through the telescope's instruments. Many of them turned out to host black holes that were rapidly consuming surrounding gas. As that material spirals inward toward the black hole, friction heats it to extreme temperatures, and that superheated material radiates enormous amounts of light outward, light that blends together with the ordinary starlight coming from the rest of the galaxy. From billions of light years away, a modest galaxy with a voraciously feeding black hole at its center can look almost identical, through a telescope's instruments, to a genuinely much larger galaxy packed with stars. The telescope measures brightness, and brightness is normally a dependable stand-in for stellar mass. Normally, in these particular cases, the black hole alone was doing the radiative work of billions of ordinary stars combined, inflating the galaxy's apparent size the way a bright flashlight taped behind a small candle can make the candle look far larger than it actually is. Once those black hole-dominated little red dots were removed from the sample, the remaining galaxies fit comfortably within what the standard model predicts. The lead researcher's academic advisor put it plainly afterward: there is no crisis in terms of the standard cosmological model, at least not one coming from these particular galaxies. But the story did not end there quite so neatly. even after stripping out every little red dot from the sample. Roughly twice as many genuinely massive galaxies remained in the early universe as the standard model expects to find. Not enough of a surplus to break the model outright, but enough to bend it noticeably. The researcher suggested that stars may simply have formed faster in the early universe than they do in the present day, that the denser conditions shortly after the Big Bang made it harder for gas to escape, a forming galaxy before it collapsed into stars, effectively speeding up the whole process. It is a reasonable explanation, grounded in real physics, but it still requires adjusting how astronomers think early galaxies grew up, and it leaves open exactly how much adjustment is ultimately going to be needed then. In early 2025, the telescope turned up something else entirely, a massive spiral galaxy, quickly nicknamed for its wheel-like structure. Observed as it existed within the first 2 billion years after the Big Bang, spiral structure does not appear overnight, building the kind of calm, orderly rotating disk that produces spiral arms requires a relatively quiet, undisturbed history, not the chaotic sequence of mergers and collisions astronomers expect to dominate a young, crowded universe. One of the astronomers involved in the discovery, based at a university in Australia, suggested the galaxy either assembled its mass in an unusually orderly way, or formed most of its stars in place without the violent collisions that typically build galaxies of that size. Either explanation runs against conventional expectations for how early galaxies are supposed to behave. Around the same time, a separate research team based in England used the same telescope to study a much larger sample, more than 250 galaxies from that same early era, and found essentially the opposite pattern. Most of those galaxies were chaotic, turbulent, clumpy systems that had not yet settled into smooth, orderly rotating disks at all. So the early universe appears to have contained both messy, adolescent-looking galaxies and at least one remarkably mature, orderly spiral coexisting in the very same cosmic era. That combination is not something the standard model handles gracefully, and that still leaves out one of the stranger findings to emerge from this wave of observations: elongated galaxies. A study published in late 2025, led by a researcher working with collaborators from institutions in the United States and Taiwan, found that a significant number of young galaxies observed by the telescope appeared strikingly stretched out, shaped less like the tidy disks or spheres astronomers expect and more like cosmic cigars. These elongated prolate shapes do not match what the leading dark matter model predicts. They do, however, match predictions made by a couple of alternative dark matter frameworks, models in which the underlying filaments of the universe's large, scale structure are smoother than the standard picture assumes, allowing gas and stars to flow along them in stretched-out streams, rather than settling into the more compact shapes the conventional model favors. That distinction matters more than it might sound like at first. The particular flavor of dark matter assumed by the standard model is not just one ingredient sitting alongside everything else. It functions as the scaffolding for the entire framework. It determines where galaxies form in the first place, how they cluster together, and what the large-scale structure of the universe looks like on its biggest scales. If the particles that make up dark matter behave even slightly differently than the standard assumption requires, if they are lighter or interact differently, or move differently through space, the consequences would ripple outward through nearly every prediction cosmology makes. It would shift the expected mass of galaxy clusters. It would change the predicted number and distribution of small satellite galaxies orbiting larger ones. a description that has already been a quiet source of tension for years. It would alter how strongly massive objects bend and distort light passing near them, an effect astronomers rely on constantly to map invisible mass across the universe. You cannot swap out the foundation underneath a building and expect the walls resting on top of it to stay exactly where they were. It would be easy to dismiss all of this as a disagreement confined to just two competing techniques, as if the whole crisis rested on a rivalry between one satellite and one research team's distance ladder. It does not. Over the past several years, astronomers have developed entirely independent ways of measuring the present-day expansion rate, methods that do not rely on Cepheid stars, supernova, or the cosmic microwave background at all, and several of them keep landing closer to the higher distance ladder value rather than the lower early universe prediction. One of these methods uses gravitational waves, the ripples in space-time produced when massive objects like black holes or neutron stars collide. When two neutron stars merged in a galaxy roughly 130 million light-years away in 2017, detectors on Earth picked up both the gravitational wave signal and a burst of light from the same event, observed independently by dozens of telescopes around the world, because the gravitational wave signal itself encodes information about how far away the source is. Astronomers could calculate the distance to that galaxy without leaning on Cepheids or supernova at all. Then combine it with the galaxy's redshift to get another completely independent estimate of the expansion rate. That single event was nowhere near precise enough to settle the argument by itself, but it demonstrated the technique works. And as detectors improve and more of these merger events get observed, this method, sometimes called a standard siren measurement because it plays a role similar to the standard candles used by supernova, is expected to eventually deliver its own independent verdict. A second alternative method relies on gravitational lensing, the bending of light around extremely massive objects predicted by general relativity. When a distant, variable light source, such as a quasar powered by a feeding supermassive black hole, happens to sit almost directly behind a massive foreground galaxy, that galaxy's gravity can bend the quasar's light into multiple separate images, each one following a slightly different path through curved space-time. Because those paths differ in length, light along one path arrives at Earth days, weeks or months before light along another path produces flickers in brightness that show up at slightly different times in each lensed image. Measuring that time delay, combined with a detailed model of the foreground galaxy's mass, lets astronomers calculate distances across billions of light-years without needing Cepheids or supernova anywhere in the chain. A research collaboration using this exact technique on a modest sample of lensed quasars arrived at an expansion rate close to the higher distance ladder value, adding yet another independent voice to the side of the disagreement that does not match the early universe prediction. A third method looks at galaxies containing something called regions where naturally occurring molecules amplify microwave radiation the same way a laser amplifies visible light, producing an extraordinarily precise geometric measurement of distance, based purely on the physics of orbital motion around a central supermassive black hole. This technique requires no calibration ladder at all, no chain of intermediate steps that could introduce compounding errors. Measurements using megamaser galaxies have also tended to land closer to the higher value. None of these alternative methods is yet precise enough on its own to end the argument. Each comes with its own uncertainties, and researchers continue refining every one of them. But their existence matters enormously. because it undercuts the simplest possible explanation for the tension, that something specific to Cepheid variables, or something specific to the way supernovae are calibrated, is quietly corrupting the distance ladder measurement. If several completely independent techniques, built on entirely different physical principles, keep converging on a similar answer, the case that the standard model itself may be incomplete gets considerably stronger. There is a second, quieter disagreement running alongside the expansion rate problem, one that most people outside the field have never heard of. Astronomers call it the S8 tension, and it concerns not how fast the universe is expanding, but how clumpy it is. Matter in the universe is not spread out evenly. Gravity has spent billions of years pulling it together into filaments, clusters, and vast cosmic voids, producing the sprawling web-like structure that shows up in every large-scale survey of galaxies ever conducted. The standard cosmological model, using the same early universe parameters derived from the cosmic microwave background, makes a specific prediction for how strongly that clumping should have developed by the present day. When astronomers measure the actual clumping directly, using techniques like weak gravitational lensing, where the shapes of countless background galaxies are subtly distorted by the mass sitting in front of them, they consistently find slightly less clustering than the model predicts. Not a dramatic mismatch, a small, persistent one, showing up again and again across independent surveys using different telescopes and different statistical techniques. Adam Rees has described this second disagreement as the smaller sibling of the expansion rate tension, less dramatic on its own, but worth watching closely. If both tensions turn out to be genuinely real rather than statistical flukes or overlooked sources of error, they may be symptoms of the same underlying problem, two separate cracks running through the same wall. A model of dark energy that behaves differently than a simple constant, for instance, or a version of dark matter that clusters slightly less efficiently than the standard assumption, could, in principle, nudge both numbers in the observed direction simultaneously. Nobody has proven that connection yet, but it is exactly the kind of pattern that tends to catch a physicist's attention, because a small tension in the expansion rate paired with a small tension in cosmic clumpiness is a lot more interesting and a lot more suspicious than either one showing up alone. None of this is the first time cosmology has faced a contradiction that seemed, for a moment, to threaten the entire framework. In the 1990s, the field nearly buckled under a different kind of crisis entirely, one that in hindsight looks almost quaint compared to what is happening now, but which felt just as urgent at the time. Astronomers had independent ways of estimating the ages of the oldest stars in the universe, based on detailed models of how stars burn through their nuclear fuel over time. Those calculations kept producing ages for the oldest known stars that were uncomfortably close to, and in some estimates, even older than the calculated age of the universe itself. That is not a subtle problem. A star cannot be older than the universe it exists inside of. Something in the underlying picture had to be wrong. Either the stellar models, the measured expansion rate at the time, or some deeper assumption nobody had questioned yet. The resolution came from two independent research teams, working separately and racing each other, who spent years searching for distant Type 1a supernova, the exact same class of exploding star used today in the Cepheid-based distance ladder. Their goal was to measure how the universe's expansion rate had changed over cosmic time, expecting to find that gravity was gradually slowing the expansion down, the way a ball thrown upward slows as gravity pulls back against it. Instead, both teams found the opposite. The expansion was not slowing. It was speeding up. Distant supernovae appeared fainter than expected, meaning they were farther away than a purely gravity-dominated, decelerating universe would predict. That discovery, announced in 1998, forced the field to accept the existence of something previously unknown, an unseen form of energy, filling all of space, exerting a kind of negative pressure that pushes space apart rather than pulling it together, growing more dominant as the universe expands and ordinary matter thins out. Physicists gave it a deliberately vague name, dark energy, precisely because nobody understood what it actually was. And in truth, nobody fully understands it today either. What they could say was that it explained the observations, resolved the age contradiction that had been troubling the field, and slotted neatly into the mathematics of general relativity as something called a cosmological constant, a fixed amount of energy inherent to empty space itself. The researchers who led that discovery shared a Nobel Prize in physics. A little over a decade later, it is worth sitting with how strange that resolution actually was. The universe had a problem, an internal contradiction between the ages of its oldest stars and its own calculated age. The solution was not a correction to the star models. It was the discovery of an entirely new component of reality, one that today is thought to make up roughly 68% of everything that exists, more than twice as much as ordinary matter and dark matter combined. What looked, for a few uncomfortable years, like a fatal flaw in the standard model turned out to be the shadow of something enormous that nobody had previously known was there. That is the pattern worth remembering here. Crises in cosmology tend to feel, in the moment, like the ceiling caving in. They almost always turn out instead to be doors. The 1990s crisis over stellar ages did not end with cosmology abandoning its framework. It ended with cosmology adding a fundamental new ingredient to it, dark energy sitting alongside. Dark matter and ordinary matter as one of the three pillars supporting everything astronomers now believe about the structure and history of the universe. Today's standard model rests on a specific accounting of what the universe is actually made of. Roughly 5% is ordinary matter, the atoms making up stars, planets, gas, dust, and every living thing, including every person who has ever watched a sunset or wondered what any of this means. Roughly 27% is dark matter, an invisible substance detected only through its gravitational pull, never directly observed, but required to explain how galaxies rotate and how large-scale structure formed in the first place. And the remaining 68% is dark energy, the mysterious pressure driving the accelerating expansion discovered back in 1998, still essentially unidentified more than a quarter century later. 3 ingredients, 2 of them given a name purely as a placeholder for something nobody has ever directly detected, measured, or explained. And now, layered on top of that already uncomfortable accounting, a present-day expansion rate that will not agree with itself, no matter how carefully anyone measures it, along with a population of early galaxies that grew up faster and stranger than the model expected, and hints of dark matter behaving in ways the leading framework did not predict. It would be reasonable to ask whether the standard model is simply wrong. Most cosmologists would answer no, not wrong, incomplete. And the distinction matters more than it might seem. It helps to understand just how much the standard model gets right before deciding how worried to be about what it gets wrong. Cosmologists sometimes refer to it by a shorthand name, built from the Greek letter representing dark energy paired with an abbreviation for cold dark matter. But the label matters less than the track record. The model correctly predicts the relative abundance of the lightest chemical elements: hydrogen, helium, and trace amounts of lithium, forged within the first few minutes after the Big Bang, long before any star had formed. That process, called Big Bang nucleosynthesis, depends sensitively on the conditions present in the first few minutes of cosmic history, and the predicted ratios match what astronomers actually observe in the oldest, most pristine gas clouds in the universe with remarkable precision. The model correctly predicts the detailed pattern of tiny temperature variations imprinted across the cosmic microwave background, variations of only a few parts in 100,000, corresponding to the seeds of structure that would eventually grow into every galaxy cluster, and every void in the observable universe. The statistical pattern of those variations, measured across the entire sky, matches the model's predictions across an enormous range of angular scales, from the whole sky down to features spanning only a fraction of a degree. The model correctly predicts, in broad strokes, how galaxies cluster together across the largest scales astronomers can observe, forming the filaments and voids that make up what is sometimes called the cosmic web. Massive surveys mapping the positions of millions of galaxies have repeatedly confirmed that the large-scale distribution of matter in the universe looks statistically very close to what the standard model predicts it should look like, given how much time has passed since the Big Bang. No competing framework proposed so far can match that combined track record. Alternative theories exist, some replacing dark matter with modified laws of gravity, others proposing exotic new particles or entirely different cosmological histories. But none of them currently explain the full range of observations the standard model accounts for simultaneously. That is precisely why the tensions described here are being treated as serious anomalies worth investigating rather than as evidence the whole framework should be discarded. A theory that gets an enormous amount right, but disagrees with itself on a couple of specific, carefully measured numbers, is not obviously broken. It is a theory that is missing something, and figuring out exactly what that something is has become one of the central projects in modern physics. This is also why the disagreement over the expansion rate carries so much weight despite being, on paper, just a 6 or 7% discrepancy between two numbers. A model this successful across so many independent lines of evidence does not typically fail by a small, precise, and repeatedly confirmed margin unless there is something specific and identifiable causing it. Small, persistent tensions are often more informative than large, obvious ones, because they point toward a missing piece rather than a wholesale mistake. The way a slightly imprecise clock can reveal something real about friction or temperature rather than simply being broken. The good news, if there is good news buried inside a cosmological crisis, is that an entire generation of new instruments is either coming online or already collecting data, specifically designed to attack these problems from new angles. Wide Field Space Telescope, named after a former NASA administrator, expected to begin science operations later this decade, has been built specifically to conduct enormous surveys covering huge patches of sky in a single exposure, roughly 100 times the field of view of the aging Hubble Space Telescope, while matching its image sharpness. Its primary scientific goals include measuring dark energy with unprecedented precision by tracking how galaxy clustering and gravitational lensing patterns have evolved across cosmic history, work that should help pin down whether dark energy behaves as a truly constant force or whether its strength has changed subtly over billions of years, a distinction that could matter enormously for resolving the expansion rate disagreement. A separate European Space Agency mission, launched in 2023, is already mapping the geometry and evolution of the universe across a huge volume of sky, imaging billions of galaxies to trace how the distribution of matter has evolved over roughly 10 billion years of cosmic history. Its extraordinarily precise imaging is expected to sharpen constraints on both dark matter and dark energy simultaneously, and its data should help clarify whether the mild clustering discrepancy described earlier as the smaller sibling tension is a real feature of the universe or an artifact of earlier, less precise surveys. A dedicated star mapping satellite, which has already spent years precisely tracking the positions and motions of well over 1 billion stars across the galaxy, continues releasing increasingly refined data sets that let astronomers calibrate Cepheid distances using pure geometry, measuring the tiny apparent shift in a star's position caused by Earth's orbit around the Sun, a technique called parallax that requires no assumptions about stellar physics at all. Future releases of that geometric calibration data are expected to remove yet another potential source of systematic error from the distance ladder, tightening the higher measurement of the expansion rate even further. On the ground, a large millimeter wave telescope perched high in the Chilean desert, chosen for its thin, dry air that lets faint microwave signals through with minimal interference, has already produced one of the most detailed maps ever made of the cosmic microwave background from the ground, complementing and cross-checking the space-based measurements made by earlier missions. Its results have nudged the early universe prediction for the expansion rate slightly upward, but not nearly far enough to close the gap with the distance ladder. Measurement on its own, and a new, large survey telescope built high in the mountains of Chile, equipped with the largest digital camera ever constructed for astronomy, has recently begun an ambitious decade-long project to repeatedly photograph the entire visible southern sky, cataloging tens of billions of astronomical objects and tracking how they change over time. Among its many scientific goals is an extraordinarily precise measurement of weak gravitational lensing across enormous swaths of sky, data that should help settle, one way or another, whether the universe really is slightly less clumpy than the standard model predicts. Taken together, these instruments represent a genuinely new era of precision cosmology, one where the question is no longer whether astronomers can measure these numbers accurately. They already can, to a degree that would have seemed impossible a generation ago. The question now is whether those increasingly precise measurements will finally converge on a single, consistent picture of the universe, or whether they will keep splitting further apart, forcing physicists to accept that something fundamental is genuinely missing from the framework that has guided cosmology for the better part of a century. It is worth pausing to appreciate why a telescope tuned to infrared light turned out to be so central to nearly every discovery described so far, both the ones that deepened the expansion rate tension and the ones that revealed unexpectedly massive early galaxies. Visible light, the kind human eyes evolved to detect, gets scattered and absorbed easily by dust. The fine particles of carbon, silicon, and ice that drift throughout galaxies, especially in the crowded, star-forming regions where Cepheid variables and young galaxies tend to be found. Infrared light, with its longer wavelength, slips through that same dust far more easily, the way a low, deep radio signal can travel through walls that would block a higher-pitched sound. That is part of why a sharper infrared telescope was expected to resolve the stellar crowding problem that many hoped would. explain away the Hubble tension, and part of why it succeeded instead at ruling that explanation out. There is a second, even more fundamental reason infrared astronomy matters so much for studying the distant universe. As light travels across billions of light years through an expanding universe, the stretching of space itself stretches the wavelength of that light along with it, a phenomenon called cosmological redshift. Light that started out as ordinary visible light, emitted by stars in a galaxy billions of years ago, arrives at Earth today stretched all the way into the infrared portion of the spectrum, sometimes stretched so far that it would be completely invisible to instruments built to see only visible light. To observe the very earliest galaxies in the universe, the ones responsible for the unexpectedly massive galaxy problem described earlier, astronomers essentially have no choice but to look in infrared. Anything more distant and more ancient than a certain threshold is simply invisible in any other part of the spectrum. This is why a telescope built specifically to excel at infrared observation, positioned far from the warmth and light pollution of Earth, equipped with a mirror large enough to gather extraordinarily faint signals from galaxies whose light has been traveling toward us since almost the beginning of cosmic time, was able to reshape to entirely different areas of cosmology within just the first couple of years of its operation. It sharpened the Cepheid measurements that deepened the expansion rate crisis, and it revealed a population of ancient galaxies stranger and more developed than anyone expected to find, all using the same fundamental capability: the ability to see deeply and clearly in a part of the spectrum that had previously remained frustratingly out of reach for most cosmological purposes. The elongated galaxy shapes described earlier point toward a question that sits underneath almost everything else in this story. What actually is dark matter? And how confident should anyone be in the specific assumptions the Standard Model makes about it? The leading candidate for decades has been a hypothetical class of particle that interacts with ordinary matter only through gravity and possibly the weak nuclear force, heavy enough and slow-moving enough that physicists describe it as cold, meaning it was moving well below the speed of light when structure in the universe first began forming. This cold dark matter picture has been remarkably successful at explaining the large-scale distribution of galaxies, the rotation curves of individual galaxies, which spin faster at their outer edges than the visible matter alone could account for, and the overall pattern of structure seen in the cosmic microwave background. Despite decades of increasingly sensitive experiments, buried deep underground to shield them from cosmic ray interference, or built to search for the particle's telltale signature in powerful particle accelerators, nobody has ever directly detected one of these particles. The evidence for cold, dark matter remains entirely gravitational and statistical, inferred from its effects rather than observed directly. A competing family of models proposes something different, a much lighter form of dark matter, sometimes light enough to behave less like a swarm of individual particles and more like a smooth, wave-like field spread across space, similar in spirit to how quantum mechanics describes very light particles as having wave properties. Under this framework, sometimes called wave dark matter or fuzzy dark matter, depending on exactly how it is formulated, the underlying structure of the universe would be smoother and less clumpy on small scales than the standard cold dark matter picture predicts. Exactly the kind of behavior that could naturally produce the elongated, stretched out galaxy shapes observed in the early universe, rather than the more spherical or disc-like shapes the Standard Model favors a related alternative, sometimes called warm dark matter, sits somewhere between these two extremes, proposing particles with an intermediate mass, light enough to smooth out some of the smallest scale structure predicted by the cold dark matter model, but still heavy enough to preserve most of its larger scale successes. This version has also been invoked to help explain persistent puzzles like the apparent shortage of small satellite galaxies orbiting larger ones compared to what the standard cold dark matter model predicts, a mismatch astronomers have been tracking for years. Independent of anything related to the current expansion rate crisis, none of these alternative dark matter models has been confirmed. Each one solves certain puzzles while potentially introducing new ones of its own, and distinguishing between them requires exactly the kind of extraordinarily detailed observations of early galaxy shapes and structure that only recently became possible. That is precisely why the elongated galaxy findings matter so much. They represent one of the first pieces of direct observational evidence, however preliminary, that might eventually help settle a debate about the fundamental nature of dark matter that has otherwise been almost entirely theoretical. Dark energy raises an equally open set of questions, and in some ways it is even less understood than dark matter, because unlike dark matter, it has no gravitational lensing signature, no rotation curve, no clustering pattern that astronomers can map directly. Its only observable effect is the accelerating expansion of space itself, inferred indirectly from how the brightness of distant supernovae, and more recently the clustering of galaxies across cosmic time, deviates from what a purely matter-dominated, decelerating universe would produce. The simplest possible explanation, and the one built into the Standard Model by default, treats dark energy as a cosmological constant, a fixed amount of energy inherent to empty space itself that never changes in strength over time or space. This is mathematically the simplest option, requiring only a single number, and it fits the majority of existing observations reasonably well. But simplicity is not the same as correctness, and several major galaxy surveys completed in recent years, using enormous three-dimensional maps of galaxy positions to trace how the expansion rate has evolved across billions of years, have returned hints, not yet definitive, that dark energy might be weakening slightly over cosmic time, rather than remaining perfectly constant. If that turns out to be confirmed with stronger statistical significance as more data comes in, it would represent an even bigger departure from the simplest version of the Standard Model than the expansion rate tension alone, because it would mean one of the three fundamental ingredients of the universe is not fixed and unchanging after all, but evolving an alternative framework, sometimes referred to under names like quintessence, proposes that dark energy is not a fixed property of empty space at all, but a dynamic field. Similar in spirit to the field thought to have driven the extraordinarily rapid expansion of the universe in the first tiny fraction of a second after the Big Bang, an era called inflation. Under a quintessence-style model, the strength of dark energy could plausibly change over time, potentially even reversing direction far in the future, or intensifying to the point of eventually tearing galaxies, stars, and even atoms apart in a hypothetical, extremely distant scenario sometimes called the Big Rip. Other theorists have proposed that what looks like dark energy might not be a new form of energy at all, but a sign that general relativity itself needs modification on the largest cosmic scales, the same way Newtonian gravity eventually needed refinement to explain phenomena it could not account for. These possibilities are not just abstract philosophical distinctions, They carry real consequences for the long-term fate of the universe. If dark energy really is a perfectly constant cosmological constant, the current best estimate points toward a universe that continues expanding and cooling essentially forever, growing steadily emptier and colder as galaxies drift beyond each other's gravitational reach and stars gradually burn out one by one across trillions of years, ending in an extremely long, slow fade, sometimes called heat death. If dark energy is instead weakening over time, the far future could look different, potentially even involving a gradual slowing and eventual reversal of cosmic expansion. If dark energy is instead strengthening, the far future could accelerate towards something considerably more violent. Nobody currently knows which of these possibilities, if any, accurately describes what is actually happening. And the same instruments now being built to resolve the Hubble tension and the S8 tension are also, not coincidentally, the best tools available for narrowing down which version of dark energy is real. There is another angle worth considering, one that connects back to the 1990s crisis over stellar ages. Independent methods for estimating the age of the universe that have nothing to do with either the cosmic microwave background or the distance ladder at all. One such method looks at globular clusters, dense, ancient collections of hundreds of thousands of stars that formed very early in the history of galaxies like our own and have remained gravitationally bound together ever since. By carefully modeling how stars of different masses within these clusters burn through their nuclear fuel and evolve over billions of years, astronomers can estimate the age of the oldest stars still visible within them. These estimates consistently produce ages in the range of roughly 12 to 13 billion years for the oldest globular clusters, comfortably consistent with, though not precise enough to distinguish between, either of the two competing values for the expansion rate, a second, completely independent method uses radioactive decay. Certain heavy elements forged inside the extreme conditions of exploding stars and merging neutron stars decay at fixed, well-understood rates over enormously long timescales. The same basic principle used to date rocks and fossils here on Earth. By measuring the ratio of a radioactive element to its stable decay product in very old stars, astronomers can estimate how long ago that material was forged, providing yet another rough, independent age estimate for the oldest visible structures in the galaxy, again broadly consistent with, but not precise enough to fully arbitrate, the current disagreement. These cross-checks matter because they demonstrate that the overall picture of a universe roughly 13 to 14 billion years old is not resting on a single fragile chain of assumptions. Multiple, completely independent lines of evidence, stellar physics, radioactive decay, the cosmic microwave background, and the distance ladder, all converge on roughly the same broad age range, even while two of those methods disagree with each other at the more precise level needed to resolve the current tension. The disagreement, in other words, is not a sign that cosmologists have gotten the big picture badly wrong. It is a sign that they have gotten good enough at measuring the details that are previously invisible 6%. Discrepancy has become impossible to ignore. To really appreciate what is at stake in this disagreement, it helps to zoom out even further to the very first fraction of a second after the Big Bang. Long before the cosmic microwave background was released, and long before any of the numbers described so far could even be defined, current theory proposes that in an almost unimaginably brief interval, something like a tiny fraction of a second, the universe underwent an extraordinarily rapid burst of expansion called inflation. stretching space by a factor so large that a region smaller than a single atom ballooned out to a size larger than the entire visible universe today. This idea, first proposed in the early 1980s, was not introduced simply because it sounded interesting. It was introduced because it elegantly solved several otherwise baffling observational puzzles. Why the universe looks almost perfectly uniform in every direction we look. Why space appears geometrically flat rather than curved. And why certain exotic particles predicted by some theories of fundamental physics are never actually observed. Inflation smooths all of that out by proposing that any irregularities present before this rapid stretching event would have been diluted into near invisibility. The way stretching a wrinkled sheet tight across a bed erases the wrinkles. Inflation also provides the mechanism believed to be responsible for planting the seeds of all future cosmic structure. Tiny quantum fluctuations, the same kind of inherent randomness that governs the behavior of particles at the smaller scales, would have been stretched by inflation from microscopic scales up to astronomical ones, effectively freezing tiny random variations into the fabric of space itself. Those frozen fluctuations became the slightly denser and slightly less dense regions that later collapsed under gravity to form galaxies, galaxy clusters, and the vast cosmic web of filaments and voids observed today. Remarkably, the statistical pattern of temperature variations measured across the cosmic microwave background matches the specific pattern inflation predicts with impressive precision, which is part of why the theory, despite describing an era of the universe's history that is almost impossible to test directly, remains the leading framework for understanding how the universe's earliest moments unfolded. This matters for the expansion rate tension because inflation, and the physics governing that first fraction of a second, is precisely the kind of place where an unknown ingredient like early dark energy could plausibly have operated. The proposed burst of early dark energy described earlier would have occurred long after inflation itself, but it draws on a similar conceptual toolkit, a temporary field or form of energy that existed briefly, altered the trajectory of cosmic history in a specific and measurable way, and then vanished or transformed into something else entirely, leaving behind only indirect fingerprints for later astronomers to try to reconstruct. The fact that physicists already have a well-established precedent for this kind of behavior in the form of inflation itself is part of why early dark energy remains a serious contender for resolving the current crisis rather than being dismissed as an ad hoc patch invented purely to make an inconvenient number go away. If the higher expansion rate value turns out to be the correct one, and the standard model needs revision to accommodate it, the consequences ripple all the way back to the very first generation of stars ever formed. Sometimes called population 3 stars, thought to have been made almost entirely of hydrogen and helium, the only elements produced in significant quantities by the Big Bang itself, before any star had lived and died to forge anything heavier. These first stars are believed to have been extraordinarily massive and short-lived compared to stars forming today, burning through their fuel in a matter of a few million years, before exploding as supernova and seeding the surrounding gas with the first heavier elements, the carbon, oxygen, iron, and everything else that would eventually go into building rocky planets, atmospheres, oceans, and every living organism that has ever existed, a universe that expanded faster than the standard model assumes, or one where structure formed more efficiently in its earliest stages, as the unexpectedly massive early galaxies seem to suggest, would imply that this entire chain of events, the birth of the first stars, the forging of the first heavy elements, the seeding of the first generation of planets, happened somewhat earlier and somewhat faster than previously assumed. That does not necessarily mean life appeared earlier anywhere in the universe. Forming heavy elements is a prerequisite for rocky planets and biochemistry as we understand it. Not a guarantee of anything beyond that. But it does mean the raw ingredients required for that possibility became available sooner than the standard timeline suggested, compressing what was once assumed to be a slow, gradual build-up of cosmic complexity into a somewhat faster, more front-loaded process. This is part of why the unexpectedly massive, early galaxies, discovered by the telescope, generated so much excitement within the field. Beyond the pure astrophysics of galaxy formation, they touch, even if only indirectly and speculatively, on questions about how early in cosmic history the universe could have first become hospitable to the kind of chemistry that eventually produces planets, atmospheres, and life. Nobody claims to have found evidence of early life itself, and nothing described in any of these studies comes close to that. But shifting the timeline for when the necessary ingredients first became available is exactly the kind of finding that quietly reshapes how astronomers think about the broader arc of cosmic history. Long before any telescope existed capable of searching for biosignatures on planets around other stars, it is worth stepping back for a moment to appreciate the sheer amount of independent checking that has gone into establishing that this tension is real, rather than some kind of subtle statistical mirage or a mistake buried in one team's data pipeline. Extraordinary claims in physics do not get accepted on the strength of a single measurement, however careful. They require repeated confirmation from multiple independent groups, using different instruments, different statistical techniques, and ideally different underlying physical principles, all converging on a similar result before the broader community starts treating an anomaly as genuinely significant rather than a fluke. The expansion rate tension has now cleared that bar many times over. The early universe prediction has been confirmed by more than one space-based mission mapping the cosmic microwave background, cross-checked by ground-based telescopes using entirely different instrumentation, and shown to be robust against a wide range of different statistical assumptions about how to analyze the data. The distance ladder measurement has been checked using multiple independent samples of Cepheid stars, cross-validated using an entirely different class of star for calibration, confirmed using observations from two separate space telescopes, built with different technology and different potential sources of systematic error, and now supported by several genuinely independent alternative techniques: gravitational wave, standard sirens, gravitational lensing, time delays, and megamaser distance measurements, none of which rely on Cepheids supernova, or anything else that could plausibly be corrupting the traditional distance ladder in some hidden, shared way. This is exactly the kind of pattern that makes physicists take an anomaly seriously rather than dismissing it. A single surprising measurement is interesting but not necessarily meaningful. A surprising result that survives being checked and rechecked by rival teams, with every incentive to find the flaw in each other's work, using methods that do not share the same potential sources of error, starts to look less like a mistake and more like a genuine signal, a real feature of the universe that the existing theoretical framework has not yet managed to explain. That is also why so many senior, extremely well-respected physicists, people who built their careers on the successes of the standard model and who have no obvious motivation to overturn it, have nonetheless started describing this disagreement using increasingly serious language over the past several years. moving from cautious talk of a discrepancy to an acknowledged tension to outright description of a crisis. In a field known for careful, understated language, that kind of escalation carries real weight. So where might all of this actually be heading? Broadly speaking, researchers see a handful of possible outcomes, and it is worth walking through them, because each one would mean something quite different for how the universe actually works. The first possibility is that the early universe prediction is the one that needs adjustment, most likely through something like the early dark energy mechanism described earlier, a brief extra burst of expansion in the first few 100,000 years after the Big Bang that nudges the predicted present-day expansion rate upward without disturbing the model's other well-established successes. If this turns out to be correct, the standard model survives largely intact, gaining one new ingredient rather than being torn apart, similar in spirit to how the discovery of ordinary dark energy itself resolved the stellar age crisis back in the 1990s. The second possibility is that the distance ladder measurement is subtly flawed in some way nobody has yet identified. Despite the extensive cross-checking described earlier, this has become progressively less likely as more independent methods, including gravitational wave standard sirens and gravitational lensing time delays, keep landing closer to the higher value, but it has not been entirely ruled out, and a genuinely careful scientist keeps this option on the table until the evidence against it becomes truly overwhelming. The third possibility, and in many ways the most unsettling one, is that both measurements are correct as reported, and the discrepancy reflects something more fundamental about how gravity, dark energy, or dark matter behaves that the standard model simply does not capture at all. Under this scenario, resolving the tension might require rewriting core assumptions about the physics governing the universe on the largest scales, rather than simply adding a new temporary ingredient to patch over an otherwise sound framework. This would be the most disruptive outcome, but also, for exactly that reason, the most scientifically exciting one, the kind of result that occasionally reshapes an entire field. A fourth, quieter possibility exists as well, that some combination of smaller effects, none large enough to explain the tension on its own, are compounding together to produce the observed gap. A slightly imperfect calibration here, a slightly incomplete model of stellar physics there, a modest revision to how the early universe parameters get translated into a present-day prediction. None of them dramatic individually, but adding up collectively into the roughly 6 or 7% discrepancy currently observed. This possibility is less satisfying from a storytelling perspective than a single, clean resolution, but it remains entirely plausible, and untangling it would require exactly the kind of painstaking, unglamorous work that most of modern physics actually consists of, far removed from the dramatic breakthroughs that tend to make headlines. Nobody currently knows which of these outcomes, or which combination of them, will ultimately prove correct. That uncertainty is not a weakness in how the science is being conducted. It is simply an honest description of where an active, unresolved area of research actually stands, and it is precisely why so many new instruments, spanning space-based telescopes, ground-based observatories, and gravitational wave detectors, are all being pointed at slightly different aspects of the same underlying question over the next several years. One detail worth dwelling on, because it addresses an obvious skeptical question, is how astronomers can be so confident these early galaxies really are as distant and as ancient as claimed, rather than being closer, more ordinary objects that merely look unusual in a single image? The answer lies in a technique called spectroscopy, which does far more than simply capture a picture of a distant object. Instead of just recording how bright an object appears in a handful of broad color filters, a spectrograph splits the incoming light into its individual component wavelengths, similar to how a prism splits sunlight into a rainbow, revealing detailed patterns of bright and dark lines produced by specific chemical elements, absorbing or emitting light at very precise wavelengths. Because those patterns are so distinctive, and because the amount by which they have been shifted toward longer, redder wavelengths directly reveals how much the universe has expanded since that light was emitted. Spectroscopy gives astronomers a far more reliable measurement of both distance and cosmic age than brightness and color alone ever could. When early candidate galaxies from the telescope's imaging surveys looked suspiciously distant and unusually massive, follow-up spectroscopic observations became the essential next step, and in many cases they confirmed the redshifts implied by the original photographs, verifying that these really were galaxies as they existed within the first several 100 million years after the Big Bang, not closer objects mimicking that appearance by coincidence. This is also precisely the kind of follow-up work that eventually revealed the little red dots described earlier to be black hole-dominated systems, rather than simply oversized galaxies. Detailed spectroscopic analysis of their light revealed the characteristic signature of gas, swirling at extremely high velocities close to a central black hole, a telltale sign that would never have shown up in ordinary broadband imaging alone. This distinction between imaging and spectroscopy matters because it illustrates something important about how this entire body of research actually gets done. It is not simply a matter of pointing a powerful telescope at the sky and reading off surprising numbers. Each striking claim, an unexpectedly massive early galaxy, an unusually elongated shape, a confirmed distance to a Cepheid variable star, has to survive multiple layers of increasingly detailed follow-up observation and analysis before the broader community accepts it as a genuine feature of the universe rather than an artifact of incomplete data or a misleading first impression. What is genuinely remarkable about this entire moment in cosmology is how the mood inside the field does not resemble anything close to panic. Reading through interviews, conference talks, and published papers from the researchers actually doing this work, the dominant tone is closer to sustained, focused curiosity than alarm. These are, after all, scientists who have spent entire careers building instruments precise enough to detect discrepancies this small in the first place. Finding a real anomaly is not a failure of that work. It is the entire point of doing it. One useful way to picture the situation is to imagine spending years assembling an enormous jigsaw puzzle, confident that the picture forming on the table matched the image printed on the box, only to discover a handful of pieces that clearly belong to the same puzzle, cut from the same cardboard, printed with the same texture, but which stubbornly refuse to fit anywhere in the picture you have already built. That does not necessarily mean the puzzle is wrong. It usually means the picture on the box was incomplete, missing some section that nobody had noticed was absent until those last few pieces revealed the gap. Cosmologists describing the Hubble tension and its related puzzles today often reach for exactly this kind of framing, treating the discrepancy not as evidence the whole picture is false, but as a sign that some meaningful piece of it has not yet been drawn in. Senior researchers in the field, including physicists who who have spent decades building and defending the standard cosmological model, have become increasingly comfortable acknowledging that something in the current picture may genuinely be incomplete. That kind of open acknowledgement from people with every professional incentive to defend the existing framework carries real weight. It signals that this is not a fringe complaint from outsiders skeptical of mainstream cosmology, but a serious concern shared by the very people who built and maintain that mainstream framework in the first place. There is also something almost humbling about the scale of what is being argued over here. A species living on a modest, rocky planet, orbiting an unremarkable star, tucked into the outer suburbs of one galaxy among hundreds of billions, has built instruments precise enough to argue seriously about whether the fabric of space itself is stretching 6% faster than a competing prediction says it should, getting genuinely worked up over a disagreement that's small on a canvas that large says something remarkable about how far scientific measurement has come in. Barely a century since the discovery that the universe was expanding at all, it is worth drawing all of these separate threads back together, because on their own they can start to feel like a scattered collection of unrelated puzzles rather than pieces of a single coherent story about the state of modern cosmology. There is the primary expansion rate disagreement itself, a roughly 6 to 7% gap between a value calculated from the infant universe and a value measured directly in the present day, confirmed repeatedly using sharper telescopes, independent research teams, and several genuinely different measurement techniques that do not share the same potential sources of error. There is the quieter S8 tension running alongside it, a small but persistent mismatch between how clumpy the universe is predicted to be and how clumpy it actually appears when measured directly through gravitational lensing surveys. A disagreement some researchers suspect may share a common root cause with the larger expansion rate problem. There is the population of unexpectedly massive galaxies discovered in the very early universe, a puzzle that turned out to be partially, though not entirely, explained by black hole-powered little red dots inflating the apparent brightness of otherwise more ordinary galaxies, leaving behind a smaller but still meaningful surplus of genuinely oversized early galaxies that current models of star formation efficiency still struggle to fully explain. There is the unexpected presence of a fully formed, orderly spiral galaxy sitting alongside a much larger sample of chaotic, still forming galaxies from that same early cosmic era. A combination that does not fit neatly into either a purely orderly or purely chaotic picture of how the first galaxies grew up. And there is the discovery of unusually elongated, cigar-shaped early galaxies, whose stretch geometry matches predictions from alternative dark matter models better than it matches the standard cold dark matter framework that has anchored cosmology for decades, hinting that the fundamental particle physics underlying dark matter itself might need revision. Individually, each of these findings could plausibly be dismissed as a curious but manageable anomaly, the kind of small puzzle that shows up regularly in any actively developing field of science and eventually gets resolved through better data or refined modeling, together arriving within roughly the same handful of years, largely from the same generation of extraordinarily capable new instruments. They paint a more striking picture, a standard model that continues to succeed brilliantly at explaining the broad strokes of cosmic history, while accumulating an increasing number of specific, carefully measured details that it cannot yet fully account for. There is also a deeper reason physicists outside of cosmology proper are paying close attention to how this all unfolds. Both dark matter and dark energy sit at an uncomfortable junction between cosmology and particle physics. Two fields that have historically developed somewhat independently, but which increasingly depend on each other for progress. If dark matter really does turn out to be a light, wave-like particle, rather than the heavier, more traditional candidate long favored by particle physics experiments, that would have consequences reaching far beyond cosmology, potentially requiring new theoretical frameworks in particle physics itself to explain where such a particle comes from, and how it fits alongside the other known fundamental particles. Decades of expensive, carefully engineered underground and accelerator-based experiments have been built specifically to search for the traditional heavier dark matter candidate, and a confirmed shift toward a fundamentally different kind of particle would represent a significant redirection of experimental effort and theoretical focus across an entire adjacent field of physics. Similarly, if dark energy turns out not to be a simple, unchanging cosmological constant, but instead a dynamic field whose strength evolves over cosmic time, that would connect directly to some of the most ambitious and still unresolved questions in theoretical physics, including ongoing efforts to unify gravity with quantum mechanics into a single coherent framework. Some versions of string theory, one of the leading but still unproven candidates for that kind of unified framework, predict an enormous landscape of possible values for a cosmological constant, with our particular universe simply happening to land on one specific value out of an almost incomprehensibly large range of theoretical possibilities. A confirmed evolution in the strength of dark energy over time would sit uneasily within some versions of that framework, while potentially favoring others, giving theorists another genuine piece of observational evidence to weigh against otherwise almost entirely mathematical and philosophical arguments. None of this is settled, and none of it should be treated as more certain than it actually is. But it illustrates why the expansion rate crisis and the related puzzles orbiting around it have captured attention well beyond the relatively narrow community of astronomers who specialize in measuring cosmic distances. A resolution, whenever it eventually arrives, is likely to ripple outward into particle physics, theoretical physics, and the broader project of understanding the fundamental laws governing reality, not just into the comparatively narrower question of exactly how fast a particular megaparsec of space is stretching apart today. So, what do scientists still not know? And what happens next? They still do not know with certainty. Whether the expansion rate disagreement reflects a genuinely new piece of physics or some subtler, still unidentified systematic error hiding somewhere in one of the measurement chains, even though the weight of evidence has been steadily shifting toward the former explanation as more independent techniques keep confirming the higher present-day value. They still do not know whether early dark energy, or something like it, actually existed, since no experiment has directly detected it, only inferred that it could plausibly explain the pattern of numbers currently on the table. They still do not know whether the S8 tension shares a common cause with the expansion rate tension, or whether the two are simply coincidental small discrepancies that happen to be showing up around the same time as instruments become sensitive enough to notice them. They still do not know exactly how much of the unexpectedly massive early galaxy population reflects genuinely faster star formation in the young universe, versus some remaining, more subtle observational bias that better data may eventually reveal. And they still do not know which flavor of dark matter, cold, warm, or wave-like, actually describes the substance that makes up roughly a quarter of everything in existence. Though the elongated galaxy shapes discovered recently offer one of the first pieces of direct evidence that might eventually help settle that question. What comes next is, in a sense, already underway. Over the coming several years, the newer Wide-Field Space Telescope described earlier will begin its dedicated dark energy survey, mapping how cosmic structure has evolved across billions of years with a level of statistical power no previous mission has matched. The European Geometry Mapping Mission will continue releasing increasingly precise data on the distribution of matter across enormous volumes of the universe. The star mapping satellite will keep refining its geometric distance calibrations. Tightening the foundation the entire distance ladder rests on, ground-based observatories will continue collecting gravitational wave events from merging neutron stars and black holes, slowly building up enough standard siren measurements to deliver an independent verdict of their own. And the large new survey telescope in Chile will spend the next decade repeatedly imaging the entire visible southern sky, generating the kind of enormous, precise gravitational lensing catalog needed to finally determine whether the universe really is measurably less clumpy than the standard model predicts. Somewhere across that combination of missions, spanning space-based telescopes, ground-based observatories, and gravitational wave detectors working together across the next decade, cosmologists expect to finally get an answer, one way or another, to the questions currently keeping this field so productively unsettled. Either the numbers will eventually converge, revealing that some overlooked source of error has finally been identified and corrected, or they will keep refusing to agree with each other, forcing a genuine revision to the standard model of cosmology for the first time in a generation. If history is any guide, and the story of the accelerating universe discovered back in the 1990s suggests it might be, the eventual resolution is unlikely to simply patch over the discrepancy and quietly restore the old picture. It is more likely to reveal something that was never part of the original model at all. Some new ingredient or subtlety in how the universe actually behaves, hiding in plain sight inside a gap between two numbers that, on the surface, look deceptively close to each other. The universe is not broken. It has been expanding, forming galaxies, and building the conditions for stars, planets, and eventually curious observers capable of measuring all of it. For roughly 14 billion years, regardless of which specific value for the expansion rate eventually turns out to be correct. What is incomplete is the map humanity has drawn of that process. A map that has already been redrawn more than once before, each time growing more accurate, more detailed, and considerably stranger than the version that came before it. If the pattern holds, whatever resolves the current tension is likely to do the same thing again. Replace a slightly too simple picture with something more complicated, more surprising, and ultimately more revealing about what this universe actually is. If you found any of this as genuinely fascinating as it deserves to be, it helps enormously to share it with someone else who might appreciate spending a few minutes thinking seriously about how fast the fabric of reality is actually stretching apart, and following along for whenever the next piece of this puzzle turns up is usually the easiest way to catch it the moment it does. For now, the honest answer is simply this: nobody knows yet, and figuring it out is exactly what a large fraction of the world's cosmologists are spending their careers doing right now, pointing an entire generation of new instruments at the same handful of stubborn, unresolved numbers, waiting to see which piece of physics has been hiding, just out of view the entire time. There is one more proposed explanation worth including, because it takes a genuinely different approach from everything described so far. The idea that our own cosmic neighborhood might simply be an unusual place to be standing, rather than the expansion rate itself being fundamentally different from what the standard model predicts. Large-scale surveys of galaxy positions have suggested that our galaxy may sit inside, or near the edge of, an enormous region of space that is somewhat less dense than the cosmic average, a vast underdensity spanning hundreds of millions of light-years, sometimes referred to as a local void. If that underdensity is real and large enough, its weaker gravitational pull would allow the surrounding matter to flow outward into it slightly faster than the cosmic average, a purely local effect that could make the expansion rate measured from our particular vantage point appear artificially higher than the true universal average rate calculated from the deep, uniform structure of the early universe. This explanation is appealing because it would not require inventing any new physics at all. No early dark energy, no modification to dark matter, nothing beyond gravity behaving exactly as general relativity already predicts, inside an unusually empty region of otherwise ordinary space. It is also, for that same reason, considered a relatively conservative explanation by researchers in the field. The trouble is that most detailed studies attempting to measure the size and depth of any local underdensity have found it is not quite large enough, nor quite empty enough to fully account for the entire 6 or 7% gap on its own, even though it might still be contributing some smaller fraction of the observed discrepancy. Untangling exactly how much of the tension, if any, comes from this kind of local effect, rather than from a genuine difference in the universal expansion rate, requires exactly the kind of enormous, wide-field galaxy surveys that missions like the new Dark Energy-focused Space Telescope and the Large Ground-based Survey Telescope in Chile are specifically designed to produce over the next several years, mapping the three-dimensional structure of the universe around us in far greater detail than has ever been possible, before it remains one of the more actively debated possibilities, precisely because it sits at an interesting middle ground, modest enough to require no revision to fundamental physics, yet still capable of meaningfully affecting how confidently anyone can currently claim to know the true universal expansion rate of the cosmos as a whole. Put all of it side by side. The expansion rate that will not agree with itself, the quieter clustering tension trailing behind it, the early galaxies that grew up too fast, the black holes disguising themselves as oversized galaxies, the lone spiral sitting among a crowd of chaotic newborns, the cigar-shaped galaxies hinting at a different kind of dark matter, and the possibility that a portion of it all traces back to nothing more exotic than the accident of where our own galaxy happens to sit. And a clear pattern emerges. This is not a single anomaly waiting for a single clever fix. It is a cluster of related, carefully measured discrepancies arriving together from the same handful of extraordinarily capable instruments at the same moment in scientific history, each one nudging at a slightly different seam in an otherwise remarkably successful theory of everything the universe is, and how it came to look the way it does. Whatever the eventual answer turns out to be, it is being worked out in real time, through published papers, competing analyses, and increasingly precise instruments, rather than behind closed doors or settled by a single dramatic announcement. That transparency is, in its own quiet way, one of the more reassuring parts of this entire story. The universe has handed physicists a genuine puzzle, one large enough and stubborn enough to have earned the word crisis from people who do not use that word lightly, and an entire generation of telescopes, satellites, and detectors is now being pointed directly at it, with results expected to keep arriving steadily across the rest of this decade. That is, ultimately, what makes this such a genuinely satisfying moment to be paying attention to cosmology, even without a tidy resolution to offer at the end of it. The questions are precise. The disagreements are measured to fractions of a percent rather than argued over in vague generalities. And the tools capable of finally settling them are not hypothetical. They already exist. They are already collecting data. And within the next several years, the universe is very likely to reveal, one way or another, exactly which piece of the current picture has been standing quietly in the wrong place all along. That is a rare and genuinely exciting position for any field of science to be standing in, and it is worth watching closely.